Welcome to my entry to the Summer of Math Exposition 2022. In this presentation I shall be asking, and mostly answering the question, what is the close but no cigar index distribution? During this time we shall consider some definitions, new and old, how I went about investigating a number sequence which I believe is new, and I end with a proposed conjecture. Hi, I'm Steve, a 60-plus retired IT project manager. I have no formal training in maths or coding and left school at 16 with basic O-level maths, so my apologies if I use any incorrect terminology or notation during this presentation. However, since the mid-1980s, I was fortunate enough to work within IT, both in private and public sector jobs. I love maths and am self-taught in areas of higher maths thanks to wonderful contributors of internet videos such as 3 Blue 1 Brown, Numberphile, The Coding Train, Mathologer and Stand Up Maths, to name but a few. I am an amateur hobby coder and generative artist. I would love it if you would visit my YouTube channel to view my art. I always welcome comments, so please let me know if you do visit, and excuse the shameless plug. So without further delay, what's this presentation all about? It started when I viewed a Numberphile video by James Grime about perfect numbers. As James explains, perfect numbers are those positive integers whose divisors add up to the positive integer itself, such as 6, which has divisors of 1, 2 and 3, which sum to 6. In reflecting on this, my interest was not focused on the perfect numbers themselves. After all, so much attention and so many articles have been written about them. They even have their own entry on the wonderful Wikipedia and appear in the equally wonderful online encyclopedia of integer sequences. By the way, both of these are great resources and deserve our ongoing support for their work. I wanted to consider the feelings of all the other numbers, the imperfect numbers. How did they feel about this? Are they happy about being imperfect? And how imperfect are they? I decided to investigate further this how close am I to being perfect matter. Not managing to find any other similar work about this, not that I'm certain there isn't any work, I just maybe didn't find it, I decided to call this the CBNC Index, Close But No Cigar Index. So the formal definition for a close but no cigar CBNC index for a positive integer would be the absolute value of that positive integer minus the sum of all its proper divisors. For example, the number 18 would have a CBNC index of 3. Here are some other examples of numbers and their CBNC index. I use absolute values for the index. I don't think it really matters if you're 3 more or 3 less than being perfect. As a side note, there are names for such non-perfect numbers. If the sum of a number's proper divisors is less than the number, it's known as a deficient number. If the sum is greater than the number, it's known as an abundant number. When I came to start to analyse this further, particularly the frequency of CBNC indexes, in other words, how many numbers have a particular CBNC index of say 1 or 2 or 3, I really had no idea what the distribution would look like. I suggest you pause the video at this point to consider this. What distribution do you think the CBNC indexes for say the first 10,000 numbers would look like? Index numbers on the x-axis and the count of numbers with that CBNC index on the y-axis. Would it be a normal distribution, random, linear from a high number of CBNC indexes of 1 and then reducing, maybe clustered around prime numbers, or even clustered around the gaps between prime numbers? With a bit of amateur coding and use of spreadsheets, I came up with a table of index numbers and their respective count of positive integers with that CBNC index. The total of numbers with a CBNC index of 0 is 4, and these are of course our friends the the perfect numbers. The total of numbers with an index of 1 is 13. That's quite a few, maybe not unexpected. The total of numbers with an index of 2 equals 8. A few less, so looking consistent. Total of numbers with an index of 3 is 1, fewer again. Total of numbers with an index of 4 is 14. A bit of a leap, but not that extraordinary. Index of 5 is 1. 9 is 0, that's our first 0. 10 is 9. Index of 11 is 0. 12 is 267. 13 is 0. Wait a minute, 12? 267? That's quite an extraordinary leap. 267 numbers between 1 and 10,000 are 12 away from being perfect. So what does the distribution look like? Using the raw numbers, the bar graph looks like this. Now quite a lot is happening in the first part of the graph, so this is an extract of the first 60 indexes. What's going on here? This deserves further exploration. Perhaps the number set of 10,000 was just too small. So I repeated the exercise with 100,000 numbers, 200,000, 300,000 and 1 million numbers. After all, it was just computer code, so tweak some variables and let it run longer, in some cases much longer. Here is a table of the results of the top 25 index numbers by count. The index 12 remains the most frequent index, although on a reducing basis by percentages. So why 12? My investigation showed that there are two types of CBNC 12 indexes. To paraphrase Orwell, all CBNC 12 indexes are equal, but some are more equal than others. 8 of these have varying formats. For example, they have different number of divisors, and as such they are much like all the other indexes. I suppose it's logical that, all other things remaining equal, statistically some numbers would have an index of 12. However, that did not account for the extraordinarily large number, and I found that some numbers with a CBNC index of 12 were special in that they shared many features, and we shall look at these in a minute. These are the 8 regular CBNC indexes of 12, all quite different. And so far these are the only regular 12 indexes I have found, and it seems logical that these in fact may be the full set. So what makes these special CBNC indexes of 12 so special? Let's look in detail at one such number picked at random, 38,838. There is a set of distinctive features of the number and its divisors. To start with, numbers with a CBNC index of 12 have 7 divisors. As noted earlier, other than the 1, each divisor is paired up with another divisor, and if 2 times 19,419 equals 38,838, it follows that 19,419 is exactly 1/2 of 38,838. And it follows therefore that 12,946 is 1/3 and 6,473 is 1/6 of the number. It also follows that if 1/2 plus 1/3 plus 1/6 equals 1, that 19,419 plus 12,946 plus 6,473 will equal our number of 38,838. As we can see, the divisors split into 2 distinct groups. The 3 large divisors in the green box add up to the number, and so it therefore follows that the 4 divisors in the blue box must equal the CBNC index, and they do indeed add up to 12. Importantly, this set of common features is true for all numbers with a CBNC index of 12. Here are some more examples. Earlier I chose at random the number 38,838. So let's quickly look at the 8 numbers sequentially before that to see what numbers with regular CBNC indexes look like. There are no patterns or distinctive features, seemingly random. Again, on a side note, it is observed that prime numbers all have a CBNC index of the prime number minus 1. That is because, for the definition of perfect numbers, the number itself is not counted in the list of divisors. So under this definition, all primes have a single divisor of 1. So we have seen that the CBNC index of 12 is special, but it's not alone. Both 56 and 992 have similar special features. Indeed, there is a link between perfect numbers and the special CBNC indexes. You simply multiply by 2. A simple link to identify, but much more difficult to explain. And to be honest, I still do not really understand why this link exists. As we did with 12, let's look at one random example of a number with a CBNC index of 56. You will see that it has very similar features. Again, the divisors split into 2 distinct groups. The 5 large divisors in the green box add up to the number. The first 6 divisors in the blue box sum to the CBNC index of 56. Again, this set of common features is true for all numbers with a CBNC index of 56. And here are some more examples. Turning now to some other related findings I made during this study. There is a direct link between numbers that have a special CBNC index of 12 and everybody's favourite prime numbers. Here are some random examples of numbers with CBNC index of 12 and their linked prime number, found as the first of their large divisors. This link becomes even clearer when you consider the prime factors of each number. All prime numbers have a correlation with a number with CBNC index of 12. Take any prime, multiply it by 6, and the resultant number will have a CBNC index of 12. Here is one extreme example using a prime number greater than 46 billion. A similar link exists with the CBNC index of 56, again found as the first of its large divisors. So in conclusion, we started by asking what the distribution of CBNC indexes would look like. If I exclude the special indexes of 12, 56 and 992 from the bar chart we looked at earlier, the revised distribution looks like this, including a trend line. Perfect numbers and special CBNC numbers are rare where compared to the quantity of other imperfect numbers. I created a grid of the first 1024 numbers. This contains 3 perfect numbers, 37 CBNC special indexes of 12, and the remainder are regular imperfect numbers with many different CBNC indexes. In closing, this has been a fascinating journey of discovery for me, and whilst most of the maths is reasonably straightforward, I hope you too have found it interesting. Moreover, I hope it might encourage others to delve into mathematical investigations. I have not found all the answers. If anyone has any insight into my unknown points, then I would be very happy to hear from you. Having found my special CBNC index of 12, I believe that, whilst the percentage count of such indexes decreases as the size of the number set increases, because these numbers with a special CBNC index of 12 are linked to every prime, no other CBNC index will eclipse it, regardless of the size of the number set. For every new prime discovered, a new number with a special CBNC index of 12 will also be discovered. Thank you for listening.